Hello and good morning everyone. Today inshallah we will continue on vector spaces. We already started this topic in the previous lecture. It's really very important to go through it with me once more. I will do the Lisbon slides today and we will go through it step by step. Okay, it's exactly the same, but I've made the introduction in the last week, in the last lecture, in order to make your life a little bit easier with the general context. Okay, about the midterm exam, the first midterm exam, it will be till the end of our lecture today. So I need you to study the previous part, mainly focus on the topics before vector spaces. If vector spaces come, it's going to be just only one question out the 5 or 4 questions that you will have in your first midterm. In the 6th week, I made a complete revision, solving the previous exams. And if you have any questions, please try to prepare them within the next lecture. I can do a revision for you, but just you will have to let me know if you want this to lose the coming lecture to be revision, or if you have questions or doubts about anything, I will be here. Okay. Today, as I told you, we will continue with the vector spaces. It will start with the definition. We already had the definition yesterday, that V is non-empty set, and we already know now that the vector spaces, it's about sets. At the worst case scenario, it's not empty because it contains the origin, okay? It's called vectors, in which we define 2 algebraic operations. This operation, which is the addition, okay? The addition between vectors, and the multiplication by scalar. Those are the definitions of the addition closure and the multiplication by scalar closure. Okay, once we go through the addition property, we have 4 main properties you will have to test if you are testing certain set to be a vector space or not a vector space. Number 1, if you have 2 vectors belongs to this set, they should commutate. Also the associativity, the existence of the origin, and every U will have a symmetric vector, which is the inverse of the addition vector. Once you add them together, the result will be the origin. Also, you will have the 4 properties regarding the scalar multiplication, the distribution of the scalar multiplication of 2 vectors, the distribution of 2 scalars on 1 vector, the associativity of 2 constants on 1 vector, and of course the identity of multiplication of a scalar, which means once you multiply a vector by 1, the result will be the same vector. Of course, we talked about that we are not talking about just only vectors. It could be vectors, matrices, polynomials, functions, as we already saw in the previous lecture. A vector space is a set, once more, it is a set of objects called the vectors, in which we define the 2 operations. You already know about this. For the spaces R to the power of n, which means R1, covering R1, R2, R3, open. Okay, the set of all ordered n tuples. And within the addition, vector addition, which means you will add the corresponding vectors. This is the main. And for a scalar multiplication, multiplying every coordinate by this value. Okay, for Rn with usual vector addition and scalar multiplication, it will be a vector space. Examples R1, R2, and R3. What's really important in this, we already covered this in the previous lecture, but also once more, what's really important is R1, we are considering the set of real numbers, Omar. R2, we are considering the 2 coordinates. What's really also important at this part is that you try to write, because you may think that you're understanding the context, but once you try to write it, you will face some problems, okay? So I want you to write the parentheses of the sets, how to identify a vector by the coordinates as it is written. So in such a case, we are defining that this R2 contains 2 coordinates, x1 and x2, such that both of them, x1 and x2, or x and y, belongs to the set of real numbers. Same way for R3. For matrix spaces, which is a matrix for any dimension, which is M and N. It's represent a vector space in general because of the addition property and the multiplication by scalar properties in matrices. So it makes sense that it is a vector space. Okay, those once more are the 8 rules that you will have to follow. Those are the 8 rules. 4 of them mainly regarding the addition of vectors, and the 4 of them about the multiplication by scalars. Polynomials is really very important, and we are focusing on polynomials just a little bit, because not every polynomial it's going to be a vector space. It's going to be a vector space under certain condition, which is you are talking about a polynomial of order R and less than that. But if we are talking about a polynomial with a specific degree, it's not going to be a vector space. So he is giving you a general form of a polynomial, a1, b1 of x, b2 x squared, b3 x cubed, and so on. All of this will go with AI belongs to real numbers, so all the coefficients belongs to the real set. The set of all polynomials with variables, with coefficients, they already obey the laws of the addition. So you have an addition closure, and the multiplication by scalar closure, so it's considered a vector space. And this is actually how to prove for a certain set of polynomials that it represents a vector space. I will have to do the addition and the multiplication by scalar. Okay, so it's certain B with usual vector addition scalar multiplication is a vector space. This is B and the set of all polynomials of degree less or equal. Remark once more, it has to be written that it is less or equal, because if this polynomial, for example, it's of order or of degree n, if I'm talking in specific about the polynomials of degree n only, it's not going to be a vector space, because it will miss the zero, okay, the zero of this objects to be a part of this vector space. So it can be a set, that's not a vector space. In order to be a vector space, especially for polynomials, it has to be the set of all polynomials, let them or equal the degree given. Okay, I've repeated this more than once because it's really very important. And also here, it's another confirmation on this fact. That's B with 0 degree. What's the 0 degree, Hussein? The 0 degree are the numbers, like 3, 4, 5, 6. Those are 0 degree polynomials. Polynomials with first degree, it's like 3 plus 2x, and so on. X squared will start. So it's already in B2, it's considering the less than degree polynomials. So if I'm talking about an x squared plus 2nx plus 4, if you are missing the value of x squared, it's a subset from the quadratic equations. You understand what I'm saying? But if I'm talking about the quadratic equations in specific, so I'm just limiting my building of this set to all the polynomials with the appearance of x squared. And in this manner, once more, you are not going to have a 0. Okay, so note that a vector space cannot be an empty set. That's V doesn't equal not to 0, but to phi. Phi means the empty set, there is nothing. But a vector space or a set can be a vector space even though if it has just only one vector, which is the origin. Okay. Since it has at least the 0 vector, the additive neutral number, if V is a non-empty set but doesn't have the 0 vector, then V is not a vector space. It's a confirmation of what we said. The set of polynomials of non-zero degree n is not a vector space, once more. So this slide is covered, it's about polynomials, and this is really very important to just keep in mind in all times. Also for function spaces, I can do the same. So let's summarize what I've said. A vector space, it's a collection of some things. They may be vectors, they may be polynomials, there may be matrices, there may be functions. But this set is a huge set, because this set should have an additive closure and multiplication by scalar closure. Once we say an additive closure, it means any two vectors or any two objects of this set, once you add them together, the result will belong to this set. This is number one, so it's a huge set. Number two, the multiplication of a scalar, and once you identify the scalar, it's a number from out of the real set of numbers, so it's going to be a huge set, okay? So it's also can be applied on functions, as we said, for function spaces. Also for f plus g of x, it means f of x plus g of x, which means the addition closure. And also if we multiply f of x by a constant, we will have alpha of an f of x, which is the scalar multiplication closure. Let V be a vector space, then the following four remarks are applied, or these five remarks are applied. So if V is a vector space, if I told you in a problem that V represents a vector space, you have the following in your mind. This is going to be known for you. For number one, the zero vector of V is zero and it is unique. So there is just only one object which represents the zero. Number two, U belongs to V, its additive inverse is unique and belongs to this set. Okay. For any vector u belongs to V, we have 0 times u equal to the origin. So if you multiply a zero scalar in a which makes sense. For any scalar alpha, we have that alpha times 0 is going to equal to 0. And of course, the existence of the inverse of any vector, or if you multiply by -1, you will get the inverse of this vector. Okay, those are the proofs. I will skip the proofs for the time being. I've already sent you the slides for this part. Those are the proofs of the five remarks that we did go through, but I don't want to lose time and also to make it complicated going through these notations. Okay, let V be a vector space and let S be a subset of V. I'm going to speak now or to talk about what's the condition of a subvector space from a vector space. A subvector space, it means a part of a vector space. So, what's the difference between a subset and a subvector space? There is differences between the two meanings. A subset, it's a part from. So when I say S is a subset from V, so S contains some elements from V, okay? But when we say S is a subvector space from V, number one, it will be a subset. So all the vectors in S already belongs to V. But with the zero vector and with the conditions of vector space. So to be a subvector space, it means this set or the smaller set is by itself a vector space. This is number one. Number two, they are sharing the same vectors. Number three, they have the same origin. This is the meaning of a subvector space. So in this paragraph, he's telling you, let V be a vector space and the S be a subset of V. So it's a part of V. Okay? That's S is a subset of V. Once more, it's a part of it. We say that S is a vector subspace or subvector space, both of them are correct, of V if S itself is a vector space. S by itself should be a vector space. Okay? Under the operation of vector addition and scalar multiplication and the sharing the same origin. We must state, sharing the same origin. So the origin of S should be the origin of the main vector space. And this is also covered in the previous lecture, but this is how it's written. Not that way, to show that any S subset of V is a vector subspace of V is to show that S is closed under the vector addition and scalar multiplication divided of V, and that it satisfies the 8 properties of the vector space, which once more confirms that S by itself is a vector space, but smaller than the original one. Okay, however, since S is a subset of W, some of these remarks are already old, which is the distributivity of a scalar on the addition, and so on. Okay, let V be a vector space and S be a subset. They should share the following. The origin belongs to S, which means the origin of the main vector space. It should be the same. Number two, U and V, it's their addition belongs to S and the multiplication by scalar belongs to S. So this is the main condition of having a subvector space. Why the topic is really very important to identify first a vector space, then a sub-vector space. Because it will appear with you with the problems. Also, I will skip the proofs, it's already there, so you can just go through it. But I will talk about some examples in order to make things a little bit easier. Okay, in this example, he wants you to consider the vector space R cube or R3. And he's giving you the set of all tuples or all coordinates, x, y, and z. Of course, R3, we are talking about 3 components. So it's an x, y, and z, and all of them belongs to R cube. Such that there is a condition for this vector space. That's x minus 3y plus 3z should equal to 0. If this, under this condition, represent a vector space, شباب انتوا فاهمين بقول ايه؟ مش واضح. زياد. الفيكتور R3 ده بيمثل فيكتور سبيس. انا مش عايز اقول بالعربي لان بالعربي يبقى شكله مش ظريف قوي. بس خليني اقول ان R3 ده هو فيكتور سبيس. يعني ايه فيكتور سبيس؟ قول لي بالعربي يعني ايه فيكتور سبيس؟
فيكتور سبيس نون امتي.
سيبك من الديفينيشن، انا عايز المعنى. ايه اللي انت فاهمه؟
هي
مجموعه كبيره قوي. مجموعه كبيره قوي. المجموعه دي اللي موجود فيها فيكتورز مكون كل واحد فيهم من كام كومبوننت؟ 3 كومبوننت. المجموعه دي كبيره جدا. ايه اللي خليها كبيره؟ لان كل فيكتور منهم، تخيل كل فيكتور منهم لو ضربته في اي رقم belongs to the set of real numbers، الريزلت هتبقى موجوده داخل الست دي. فانت بتتكلم على انفينيتي من نمبر من اوبجكتس. اوكي كده؟ ده كده بيريبريزنت فيكتور سبيس. في الاديشن كلوجر، يعني اي 2 فيكتورز تجمعهم الريزلت بتاعتهم موجوده يا عمر. واي واحد تضربه في رقم الريزلت موجود. انا بقى بدرس حاجه ثانيه من الار 3 ده. طبعا حاجه ضخمه جدا. انا عايز ادرس المجموعه اللي من ار 3 اللي لها شرط، لا ما تقولش. اللي لها شرط. ايه الشرط؟ بص كده، ان اكس ناقص 3 واي زائد 3 زد بيساوي 0. عمر سيبني واي. طب معلش بس في الحته دي وبعدين اعمل اللي انت عايزه. يبقى تاني وانس مور، انا عندي ار 3 خلاص كلنا متفقين ان هو يعتبر فيكتور سبيس. انا بقى عايز من ار 3 ده عمر، عايز من ار 3 ده جزء محدد منه. الجزء المحدد ده لازم يبقى فيه الخاصيه الاتيه. لازم to prove the following property. ان x minus 3y plus 3z must equal to كام؟ to 0. يبقى انا مش بتكلم على كل الار 3، لا انا بتكلم على مين؟ على مجموعه فيه. على فكره المجموعه دي بتريبريزنت بلان مستوى، يعني زي التيبل دي، بس انا مخليه عندي بالاوريجن. هو ده اللي بيعمل المعادله دي. تمام؟ ده شكله جيومتريكال. طيب يا ترى ده بيريبريزنت فيكتور سبيس ولا مش بيريبريزنت فيكتور سبيس؟ لو عايز ادرس دي يا زياد اعمل ايه؟ يعني عايز اجاوب على السؤال ده، هعمل ايه؟ لازم اتست الثمان بروبرتيز. يبقى انا ايه اللي انا هعمله؟ هفترض ان عندي x1، شوف التجربه حاجه سهله قوي تافهه جدا. هفترض ان انا عندي x1 y1 z1، يبقى ده فيكتور صح؟ وافترض عندي فيكتور تاني اللي هو شكله عامل ازاي؟ x2 y2 z2. كل اللي هيحصل اروح جاي واخد x1 y1 z1 وعامل بيه سبستيتيوشن، واخد x2 y2 z2 واعمل بيه سبستيتيوشن. لو انا عملت بروف انه لو عوضت بالفيرست بوينت والسكند بوينت هيساوي الصم بتاعهم، يبقى خلاص بيساوي بيكوال تو 0، يبقى كده خلاص. يبقى كده عملت اديشن كلوجر. اهو ستيب باي ستيب. بص كده، show that this set is a vector subspace of V. وريني ان دي المجموعه اللي بتحقق ده هي جزء من الفي. اول حاجه عايز اوضح ان الاوريجن بتعدي بده، ودي سهله قوي ان انا اوضحها. بص كده يا عمر، لو فرضت الاكس والواي والزد هما بينتموا للار 3، يعني الاكس بتنتمي للريال نمبرز والواي بتنتمي belongs to real numbers والزد belongs to real numbers. If I substitute with 0 0 0, the result will be 0, which means the origin already belongs to this, satisfy this condition. So this is check number 1. Number 2, I will have to check the addition. And this is how to prove this. all I have to do is just to use the point x1, y1, z1, and the point x2, y2, z2. All you have to do is to substitute twice in this equation. This is what I did. This is first thing. Firstly, the substitution was x1, y1, z1, x2, y2, z2. Then I will substitute in the main equation here in x1 plus x2, y1 plus y2, z1 plus z2. If I reach the same shape and it's equal to 0, then we are done. This is the addition closure. So I will do it simply, really very simple. Start substituting. So I will have x1 minus 3y1 plus 3z1. Then I will have x2 minus 3y2 plus 3z2. Then I will take common and rearrange them. Are you with me? If I did this, then I will have the same equation exactly. Left hand side, right hand side. And both of them equal to 0. So it is proved. Also, if I want to prove the scalar multiplication, if I have this equation, x1 minus 3y1 plus 3z1 multiplying alpha, it is not going to change. It's going to be alpha x1 minus 3y1 plus 3z1 equal 0 times alpha. So 0 times alpha is equal to 0. So the equation will be satisfied in the addition closure and in the multiplication of scalar. And already the 0 exists. This is the second case. All of what I said has to be solved by hand. If you look at it at the first, now you understand. I believe you can understand it. But I will have to do it with my hand. Okay? So I will start with you once more. How to prove this relation is a vector space. So I will write Ziad. First step, checking the origin of R3. What's the origin of R3? 0, 0, and 0. So first step, I will write the equation, the condition. The condition states x minus 3y plus 3z. I will use the origin. Once you use the origin, it's going to be 0 minus 3 times 0 plus 3 times 0, and the result will be 0, which is correct according to this condition. So the origin belongs to this to this plan. Okay? So condition number 1 satisfied. For condition number 2, which mainly the addition closure of two vectors. I will use the two vectors, which are x1, y1, z1, x2, y2, and z2. Okay? I will make the substitution using these two vectors and see if the result satisfies the equation or not. Okay, start. So it's gonna be x1 minus 3y1. Of course it will satisfy. Minus, plus 3z1. Then you will add on it the second vector, which is also simply, it's gonna be x2 minus 3y2 plus 3z2, which is really very simple to take x1 plus x2 as a common, take negative 3 as a common, you will have y1 plus y2, take positive 3 as a common, you will have z1 plus z2, which exactly like substituting in this equation by the value of x1 plus x2, y1 plus y2, z1 plus z2, and so the result will equal to 0. Okay? So that's the addition closure. That's the addition closure. The multiplication by scalar, which is the third condition. This is the third condition. So all I have to do is to check that alpha times x1 already satisfy the equation. Since the equation is, once more, x1 minus 3y1 plus 3z1 is equal to 0, if you multiply by any constant alpha, the result will be satisfied by logic. So it's gonna be alpha of an x1 minus 3 alpha of y1 plus 3 alpha of z1, and so on, alpha times 0, which is equal to 0. So the third condition also is satisfied. This is how to prove
انا عشان اجاوب
The multiplication.
عدى على 8 conditions.
if it was by logic satisfying, well, by logic satisfying, I don't have to test all of them. Because alpha will answer all the probabilities of the addition and the scalar multiplication. It's a polynomial of first degree, so logically it will satisfy. Okay. هقول لك امتى بقى عندي بالثمانيه دول واشوف الفيليرز بتاعتهم، ماشي؟ طبعا ده الاكزيستنس اوف زيرو از اي تولد يو، ده التشيك بتاع الاديشن، ده التشيك بتاع المالتيبليكيشن. واتس ريلي امبورتنت، المهم هنا انك لازم تستخدم ايه؟ شباب انا عارف انه ممل بس لازم تعمل ايه؟ لازم تكتبه، لان اللي بيحصل انا فهمت خلاص الموضوع سهل، الصفر موجود، المجموع موجود، الضرب في رقم موجود، صح كده؟ بس انك تكتبه مش هيبقى سهل، ماشي؟ انزل. طبعا S1 is a vector space. طيب بص على السبست الثانيه دي، شباب بص لي على السب فيكتور سبيس الثاني. برضو انا هنا بتكلم بالصدفه على مين؟ R3 X Y and Z belongs to R3. بس الكونديشن المره دي ايه؟ انا هتكلم على الست اللي مش فيها اكس مش عارف ايه، لا بتكلم على الست اللي فيها لازم الاكس ايكوال لواي ايكوال لمين؟ للزد. يبقى الكونديشن اللي عندي المره دي ان اكس از ايكوال تو واي از ايكوال تو مين؟ تو زد. يعني ايه شكلها؟ يبقى شكلها عامل ازاي يا محمد الست دي؟ هي ست بوينتس 1 1 1 2 2 2 3 3 3 4 4 4 نيجاتيف 1 نيجاتيف 1 نيجاتيف 1.
حمل اول حاجه،
مش كده؟
حمل اول حاجه.
يبقى طيب وده عباره عن خط، كلامك صح. طيب في نقطه ثانيه بالنسبه للست اللي انا بتكلم عليه، الست اللي فيه الكونديشن ده does it have a zero؟ ينفع يبقى فيها زيرو. 0 0 0. طيب هو ال 0 0 0 ده مش هو ده الاوريجن بتاع R3؟ يبقى نمبر 1 تشيكت. نمبر 2 لو انا عندي any 2 points belongs to this straight line if the result gonna change، يعني لو انا عندي 1 1 1 جمعته على 2 2 2 the result will be 3 3 3 صح؟ طيب لو انا عندي 4 4 4 جمعته على نيجاتيف 1 نيجاتيف 1 نيجاتيف 1 it's gonna be 3 3 3 so the addition probability already exists صح؟ طيب الكونديشن اللي بعده لو انا عندي بوينت 1 1 1 1 ضربتها في 5 هيديني الريزلت بكام؟ 5 5 5 which means also the probability exists. So all the 8 conditions are satisfied. بص زياد once more the zero vector already exists. طبعا بص هو بالنسبه لنا هو بيحب يكتبه كده بس انا ممكن ما اكتبوش كده. انا اقدر اكتب ده بشكل تاني. بصوا ده خلاص اقدر امسحه. بص ده اقدر امسحه.
addition closure of ايه؟
addition closure of two vectors.
Two vectors.
Or the addition closure. You don't have to write it exactly the same. And the multiplication of a scalar closure. ماشي؟ اوكي. طيب تعالى بص على الفيكتور ده. لو انا بتكلم على S2 انا ممكن استخدم الست اللي هي x وx وx. اوكي؟ الست اللي انا استخدمتها واللي انا كتبتها دي satisfy الكونديشن اللي هناك. مش انت عندك x بيساوي y بيساوي z؟ طيب انا عملت سبستيتيوشن، شلت الواي وحطيت x فاليو وشلت الزد وحطيت x فاليو. ده نفس المعنى ان الاكس والواي والزد مالهم؟ بيساووا بعض. From this definition اقدر اقول such that x belongs to r. كمان شويه هنفهم ان انا اقدر استخدم 1 1 1 times x and such that x belongs to r. already هو عامل ده بس هو دايما بيحب لما يجي يكتب بيقول بلس الزيرو، فاهم؟ بلس زيرو. I don't have to. انا مش لازم اعمل كده. يعني مش لازم لما اجي اكتب الست دي اكتب 0 0 0 plus x times 1 1 1 such that x belongs to r. I don't have to. ليه؟ لأن already by knowledge x belongs to مين؟ set of real numbers. والست بتاعت الريال نمبرز داخل جواها مين مستر حسين؟ الاوريجن. بس ده ستريس انه at the worst case scenario it's not gonna be an empty set. It will contain دايما مين؟ الاوريجن. معايا؟ فطبعا الفيكتور existence of a zero. هنا برضو لو خدت 2 points x1 y1 z1 x2 y2 z2 وعملت بيه substitution هيطلع الثلاثه بيساووا بعض. multiplication by scalar let alpha belongs to r لو انا عندي x y z وضربت يبقى alpha x هيساوي alpha y هيساوي alpha z which belongs to s2 so it's a vector space. تعالى نحل some solved exercises علشان to solidate الميننج اللي احنا بنتكلم فيه نكمله شويه. برضو عايز ادي لك سمري تاني. انا عارف ان الجزء ده زي ما بقول لك ايه رخم من الديفينيشن بتاعه، لكن كل اللي انا قلته من البدايه once more يعني ايه فيكتور سبيس؟ ست. الست دي ايه ظروفها عشان تبقى فيكتور سبيس؟ رقم واحد اديشن كلوجر صح، اديشن كلوجر مالتيبليكيشن بسكال خلصت. طيب الحته اللي في ظهرها إيه؟ كان فيهم بروبرتي باي لوجيك اوكي انه يو بلس في هيساوي الريزلت belongs to the same factor، فده بيكون بالجنرال ديفينيشن اوف ان اديشن اوريدي اندرستود. هم 10 ممكن نخليهم يبقوا 8 مش فارق 2 بروبرتيز.
احنا ثالث ستيب عملناه كان المالتيبليكيشن باي سكيلر.
مالتيبليكيشن باي سكالر فاليو. اوكي طيب عشان يبقى فيكتور سبيس ايه اللي انا بتشيك؟ 3 حاجات. ايه الثلاث حاجات؟ الاوريجين نفسه بتاعت الفيكتور سبيس والاديشن والمالتيبليكيشن. تعال نشوف بقى امثله. هنا بيقول لك وريني اثبت لي ان الست of m matrices okay of all m by n matrices with the usual sum and scalar multiplication. يعني ايه with the usual sum and scalar multiplication؟ يعني بالديفينيشن العادي بتاع الاديشن والمالتيبليكيشن بالسكالر. هو ممكن الديفينيشن ده يتغير؟ يعني لذلك انا هنا بدات السلايدز دي اقول لك البلس في الفيكتور سبيس بتاع في it means ان التو فيكتورز انت بتعملهم ايه؟ addition to each other. على فكره الاديشن ساين دي انا ممكن اغير المعنى بتاعها في بعض الفيكتورز التانية في بعض السبيسز الثانيه. يعني تبقى علامه البلس دي مثلا ليتس سي البلس ده معناه انه الفيكتور الفيرست فيكتور will be added to twice الفاليو بتاع السكند فيكتور واسمي ده الاديشن. يبقى احنا نتفق كده مع بعض ان الاديشن بره هنا في الطرقه اجمعهم على بعض، لكن الاديشن جوه الاوضه دي اخد الفيكتور الاولاني اجيب الفيكتور الثاني اضربه في الثاني اجمعهم على بعض. دي انا سنه تمثيل. لذلك هنا هو قال لك لا احنا هنمشي على الديفينيشنز الجنرال اهو. بص بقى with the usual sum and scalar multiplication العاديين اللي احنا كلنا عارفينهم يا جماعه. اوكي ازاي اثبت دي؟ كل اللي عليا ادي الثمانيه بروبرتيز شايفهم؟ دول الثمانيه بروبرتيز. لو سمحت اكتبهم تاني بس وانت بتكتبهم ما تكتبهمش فاكتورز. عيد الكتابه بالظبط على انهم ماتريسيز. By logic for the properties of matrices it will be correct. يعني ايه الكلام ده؟ الكلام ده يعني اكتب ايه ولا اعمل ايه؟ يعني لو انا حبيت to prove these relations كل اللي انا هقوله او اللي انا هعمله في البدايه according to the normal addition and scalar multiplication in matrices. Number 1, A and B belongs to the set of m by n of r. يعني ايه المعنى اللي انا كتبته؟ ايه اللي انا كاتبه ده؟ معناه بدل ما كنت بقول u and v belongs to v capital انا دلوقتي بختار ال A وال B belongs to the set اللي هو بيشتغل عليها. مين الست اللي بيشتغل عليها؟ الست اللي بيشتغل عليها it is the set of all m by n matrices of real numbers. يبقى انا حددت ال A and B. كل اللي هيحصل هكتب دول من الاول بس هاجي اكتبهم كده A plus B is equal to B plus A بعدين for every A and B belongs to the set n of m by n. ادي الفيرست probability. لوجيك. لان ده منطقي according للنورمال اديشن. انت معايا يا مستر زياد؟ مش انت عندك اي تو ماتريسيز بجمعهم ازاي على بعض يا حسين؟ بجمع الكورسبوندنج elements. فانا عادي جدا عارف ان ال A بلس B هي ال B بلس B بلس ال A لما تجمع الكورسبوندنج elements. طيب ستيب نمبر 2 هروح طالع فوق كده قايل له A B و C كمان يا سيدي. يقوم لما هاجي اكتب الاسوشيابيلتي كل اللي هيحصل بدل ما ده مكتوب انه فيكتور هكتبه ايه؟ از ماتريكس. طبعا. يبقى اذا ده معناه ان A بلس B معايا يا شباب بلس C will equal to A بلس B بلس C. وده الاسوشيابيلتي. طبعا ال A وال B وال C نفس الكومنت ده for every A B C belongs to the set of an M by N of R matrices. By logic, according to the addition property matrices, it's correct. همشي واحد اعمل فيه نفس الكلام. يعني معناها ان انا هاجي هنا هروح كاتب there exists zero matrix belongs to M, the set of M by N matrices. معايا؟ and وهكمل. Existence of addition for every A belongs to V, there exists negative A. وده بيولوجيك. اي ماتريكس موجوده بالدايمنشن M N لها نيجاتيف فاليو M N لو جمعتهم على بعض هيبقى الريزلت بتاعهم بكام؟ بزيرو. برضه بالنسبه للبروبابيلتيز دي، لذلك السؤال ده سهل جدا. كل اللي هيحصل ان انا هعيد الكتابه بتاعت الماتريسيز اللي موجوده، بس الكتابه بتاعت الماتريسيز اللي موجوده ازود عليها المين ديفينيشن اللي فوق. طيب ده بالنسبه للبروبلم 4.1. بص على بروبلم 4.2 وبيولوجيك الاول قبل ما تبروف ات. بيقول which of the following subsets are vector subspaces of the set of n by n. which of them انت جاوبني. ها زياد معايا؟ بص كده which of the following subsets are vector subspaces of the set of m by n matrices. Number 1 حسين